Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will first briefly look at reflection of uniform plane waves from multiple boundaries and see how you can use the concepts from transmission line theory in order to solve this problem. And after that, we look at energy flow from a uniform plane wave. We discuss the concept of Poynting vector. This is the problem that we want to solve. So, you have three regions, let us say, of space, each having an impedance which is distinct from each other. So, you have impedance of the medium 1 to be eta 1, impedance of the medium 2 which is have of a thickness d, meters, micrometers, nanometers, whatever the appropriate units of meters that you have chosen, and units of distance that you have chosen, and the third region having an impedance of eta 3. So, if you were to go with the pure wave based approach to solve this problem, you would have had an incident wave normally, that is the angle of incidence and the normal to this interface would be equal to 90 degrees. So, we consider wave incident first travelling in the medium 1 and incident on the boundary between medium 1 and 2. Okay. So, if you want, you can label this boundary at say z equal to 0 and the other boundary between 2 and 3 can be labeled as z equal to d. So, as I was saying, if you go purely from the wave perspective, you have an incident electric field, right, and because eta 1 is not equal to eta 2, there will be a reflection at the first boundary itself. Of course, there will be partial transmission into the second boundary. We have calculated what is the reflection coefficient from the first medium to the second medium, which in this case, because there are multiple boundaries to consider, I have just indicated with a subscript 1 and 2 the corresponding reflection coefficient. Similarly, there will be a corresponding transmission coefficient from medium 1 onto the medium 2, and this is how the new wave, which is still uniform plane wave of the same frequency, will begin to travel. As it travels, it picks up a phase of e power minus j beta times d. Here beta is the propagation constant for the second medium, therefore I should write this as beta 2 times d. Okay. At this point, what happens? You will have one more reflection because the medium impedance eta 2 is in general not equal to eta 3. So, there is one reflection over here and a subsequent transmission into the second medium. The transmission coefficient will be tau t23 and the reflection coefficient here between medium 2 and 3 will be gamma 23. Okay. While the wave is travelling back, it picks up another phase factor of e power minus j beta 2d. Thus, if you are looking from the boundary between 1 and 2, the wave has actually completed a round trip propagation with a total phase change of e to the power minus j 2 beta 2 into d, or rather the phase change of 2 beta 2 into d. So, there will be another phase factor, but at this point our work is not complete because you will have a reflection into this second medium back and a transmission into the first medium. The transmission into the first medium from the second medium will be denoted by the coefficient tau 21 and the reflection coefficient here is gamma 21. 2 indicates the first medium, 1 indicates the second medium, and this cycle goes on infinitely, right, because there are an infinite number of times that this wave has to travel from the medium 1 medium boundary to the other medium boundary. And if you want to find out what is the overall field that is reflected in the first region, then you have to sum all the partial waves that you get from the first reflection, from the second reflection, from the third reflected and transmitted, and so on. So, you have to sum all the partial waves. Similarly, if you want to find out what is the total transmitted field, you have to sum all the partial waves that go into the third medium. Now, you can do that and you can develop what is called as a power series approach for this problem, but we remembering the ideas from transmission line theory can solve this problem with much simplicity. Okay. So, our idea would be to employ the fact that linear, isotropic and homogeneous medium of impedance eta 1 can be considered as a transmission line of characteristic impedance eta 1. So, this is the characteristic impedance ZO1, or here Z0 is the characteristic impedance, 1 corresponds to the first medium, and the characteristic impedance of this medium is obviously equal to eta 1. Then you have a second transmission line which is not infinite in extent, but it is a finite length transmission line, right. So, this finite length is of length d in meters as I told you earlier, whereas the characteristic impedance of this one is given by eta 2. Okay. The boundary between 2 and 3 will need one more transmission line to be written, but luckily for us this third medium extends all the way to infinity, which means if I look at what is the input impedance from the edge of the second to the third boundary condition, if I just look at into the third medium, this entire thing would appear to be a lumped impedance of value eta 3. So I actually have, instead of a transmission medium, I actually have a lumped impedance of eta 3. I am assuming all lossless media, therefore eta 1, eta 2, eta 3 are all real quantities. Now, how do I obtain what is the amount of reflected power, or how do I obtain what is the overall reflection coefficient? This problem of transmission line we have already solved many times. We have solved. You can in fact employ Smith chart approach in order to solve this problem. What you will be doing is to first transform this impedance eta 3 through the transmission line of characteristic impedance eta 2 and the distance of d. Okay. So, in order to get an effective impedance, which we will call as effective impedance here, effective input impedance, which acts as a load to the first transmission line. So, now the overall reflection coefficient, which I will denote by gamma over all, will be given by eta effective minus eta 1 divided by eta effective plus eta 1. Isn't it very simple? In case it turns out that your eta 3 is not real, if it is complex, there is no problem, the procedure remains the same. And if you are not going to use any equation to convert eta 3 to eta f, you can always use Smith chart, right, to convert this particular impedance from eta 3 to eta whatever that value. So, you first find out or normalize eta 3 to the transmission line characteristic impedance of eta 2, maybe that is located at this point. You know what is the length d, of course you should know what is the wavelength of operation, that should be specified as part of the problem. So, on the SWR you move an appropriate distance, land at a new point, and then from that new point, so this is the distance d that you have moved, and the new coordinates at this point marked in red will tell you what is the effective impedance. Once you found that one, you can find what is the overall transmission or overall reflection coefficient. Now, these type of problems arises quite naturally, especially in optics community, when you are trying to match two media. Okay, you have a medium and then you have, let us say, a mirror. Okay, and you want these to be matched in such a way that there should be no reflected light, or not a mirror or some other transmission optical element where there should not be any reflection at that particular wavelength. Okay, so these are what is called as anti-glare or anti-reflection coatings, which you will sometimes see on the mirrors or on the optical elements, okay, such that they block all reflection into the first medium, and therefore there is complete transmission into the second medium. But you have to coat the material with a certain coating which is called as the AR coating. So, let us say this is the medium that you have. So, let us say this is glass, and at that particular wavelength, some lambda 0, you want no reflections into the first medium. So, you simply take a certain amount of thickness, okay, and then coat this one. This will have a certain impedance eta. The impedance of the glass, let us say, is eta g, and when you shine light from the first medium of impedance eta 1, then there will be no reflections. So, no reflections are possible because you have this anti-reflection coating created. Of course, the drawback of this one is that it works only at a particular wavelength, and therefore does not really eliminate reflections if you happen to use different wavelength. Okay. So, in fact, as you change the wavelength, the amount of reflection magnitude will actually start to increase. We will have more to say about this type of reflection and how to design anti-reflection coatings, or how to design filters called as Fabry-Perot filters in a special case study module that we will talk about it later. My goal now would be to discuss the power flow, right, and I want to do that one by the help of what is called as Poynting vector. The idea of Poynting vector is very simple. We assume that there is a certain region, okay, and in this region there are some electric fields, there are magnetic fields, okay, and if possible the material also has some surface current density J, indicating that the material could be conductive or have some amount of conductance associated with that one. So, this region can be assumed to be closed, okay, having a closed surface S and a volume that is quite large. Okay. Now, we have couple of equations, right. So, we have the curl equation which tells you, curl equation for the electric field, which is del cross E equal to minus del B by del T, and then you have curl of H equal to J. I will not eliminate J because I just said that you can have some amount of conducting material out there. So, J plus del D by del T. Further, I will consider a material medium such that D is equal to epsilon E and B is equal to mu times H, where epsilon is the permittivity and mu is the permeability. I am assuming that the medium is linear, homogeneous and isotropic. Okay, so linear, homogeneous and isotropic medium. Okay, so we have del cross E and del cross H. What we do is an interesting thing. We take the electric field quantity E and dot on both sides to this del cross H equation. Okay. So, we take electric field E and dot on both sides. So, this is what happens after you take E and then dot it on both sides. Then you have H, okay, which I will dot on both sides. So, I have minus H dot del B by del T on the right hand side. Now, what I do is I simply subtract these two equations. Okay. So, I subtract the second equation from the first equation and therefore, I obtain H dot del cross E minus E dot del cross H to be equal to minus H dot del B by del T minus E dot J, and then I have minus E dot del D by del T. Okay. So, I have 3 terms on the right hand side, I have 2 terms on the left hand side, but I can actually employ a relationship, okay, which allows me to simplify this equation into del dot E cross H. Okay. So, this equation that I have is del dot E cross H. So, you can simplify the left hand side equation by using a vector identity, which we will not prove of course, but H dot del cross E minus E dot del cross H is actually del dot E cross H. Okay. So, these are the point relationships. On the right hand side you have the 3 terms. Okay. So, term 1 plus term 2 plus term 3. The first term is H dot del B by del T, the second term is E dot J, the third term is E dot del D by del T. Let us look at this term little more carefully, the E dot del D by del T term. I know that D is equal to epsilon times E, therefore, E dot product with del D by del T can be written as E dot del E by del T, and epsilon that actually comes out because I am assuming epsilon to be a constant. Now, this E dot del E by del T from differential equations or from the differentiation rules will be, or you can show that this is actually equal to del by del T of magnitude E square. Okay. So, you can show that this is equal to magnitude E square because magnitude of E square is E dot E itself. So, you simply take this one, and of course, it is because it would be twice. So, you have to put a half factor to this, and there is an epsilon term here. So, instead of retaining the epsilon term as a constant outside, I can even put the epsilon term inside. So, eventually obtaining for this entire term on the right hand side to write this one as half del by del T epsilon magnitude of E square. Okay. Similarly, you can show that H dot del B by del T can be written as half, rather this is not del by del T, this is d by dt, or d by dt, del by dt does not matter in this particular case. So, I have d by dt of epsilon magnitude of H whole square. Okay. We have not really talked about it, but there is a quantity called as electric energy density, okay, which tells you how the electromagnetic energy is actually stored in the form of an electric field. Okay. And strictly speaking, applicable only for the static electric field, but luckily these concepts are also applicable for the time varying case that we are considering here. Okay. In the static case, you do know that the electric field, electric energy density can be written as half epsilon E square. Okay. This half epsilon E square, the intuition to that one is the half CV square term, and if you know that capacitance is primarily an electrostatic concept, then this half epsilon E square kind of makes sense. Similarly, an inductor stores an energy of half Li square, okay, and the corresponding energy in the magnetic field, it stores it in the form of a magnetic field because inductance is primarily a concept associated with the magnetic field or magnetostatic field, and that would be half mu h square. So what you are looking at is the rate of change of electric energy density because these are defined over a very small volume that we have taken, and the rate of electric energy density change or the rate of magnetic field density, that is the rate of change of electric energy density or the magnetic energy density should tell you about the power that is increasing, right. So in a closed surface, if you say that there is an energy or the rate at which the electric energy density and the magnetic energy density that is present inside is increasing or decreasing depending on the sign. For increasing, we keep the sign as plus, for decreasing we keep the sign as minus. Okay. So essentially there is some power change or energy density change with respect to time that is happening. Now I write WE as half epsilon E square. So I have removed that magnitude term. I am assuming that when I write E without any vector sign, this actually points to magnitude itself. Okay. So you have half epsilon E square, and similarly the magnetic energy density is half mu h square, and the terms that you had, d by dt or del by del t terms you had were del by del t WE plus del by del t Wm. Of course, there is an overall minus sign because this is how they were in the right hand side of the equation. Well, we have not forgotten the other term. We have E dot j, but since j is related to electric field in terms of the conductivity, so this can be written as sigma E square, right, because j is equal to sigma times E, and E is the magnitude in this particular notation. Therefore, E dot j will be equal to sigma E square. To that again, or we will add this term also to the right hand side. So you have a plus sigma E square, and these are all the energy density quantities. Okay, these are all the energy density or the rate of change of this energy density vectors. What is the left hand side here? Left hand side is del dot E cross H. Now I can apply Stokes theorem, okay, to the entire closed surface that we had considered and integrate this out over the volume. So if I integrate this one, I have del dot E cross H, okay, dV, that is the first integration that I have to do. This should be equal to minus del by del T WE plus del by del T Wm plus sigma E square, this entire thing integrated over the volume, because the quantity inside is all energy density term multiplied by the volume will give you the total energy. So energy density measured in terms of volume multiplied by the volume itself will give you the total energy. I am not yet done. As I said, I apply Stokes theorem to this one and convert integral of del dot E cross H to dV as integral over the closed surface of the quantity E cross H dot ds, where we considered the surface, right. This was the surface that we considered, and this would be the normal to the surface, and this itself had a volume of V over which we are actually integrating on the right hand side. So this quantity, let me remove the minus sign over here, or maybe I can keep minus sign, doesn't matter. So this should be equal to integral over the minus sign a volume, okay, then d by dt or del by del t, doesn't matter, plus Wm, which tells you how the total electromagnetic energy is changing, plus the energy that is actually getting dissipated because of the presence of non-perfect conducting material, integrated over the volume. Now look at this right hand side. It tells you that in a closed surface, in that volume that is enclosed by the closed surface, the electromagnetic energy is decreasing the rate of electromagnetic energy is negative, which means electromagnetic energy is decreasing with time, and there is also dissipation in the form of the ohmic loss by this sigma E square by heating of the material. So even that power is actually reducing. So if in a closed surface, if the power or if the energy density is decreasing, then obviously something must be coming into it, right? So some other agency must actually send that amount of energy, so that energy actually drains out. This was like, inside a closed surface, charge is melting away, but if the charge is melting away, someone has to put the charges in order to maintain the continuity, and putting the charge means that the current was flowing into it, right? So that is the meaning out here. If you change the minus sign onto the left and to the right, okay, then the negative sign onto the left will tell you that this energy is actually coming out, okay. So in essence, this term E cross H, okay, so this term E cross H is actually describing the way the electromagnetic energy, not always but most cases, yes, the way the electromagnetic energy is changing, okay. You are not content with having E cross H, because you do not want the instantaneous energy, or this E cross H will always tell you the instantaneous energy that is flowing, but you want a time averaged energy, right, or you want a time averaged power. So if you assume that electric field is sinusoidal, magnetic field is sinusoidal, then you can show that the time averaged Poynting vector, okay, where the Poynting vector S is defined as E cross H, and E cross H tells you that there is a power outflow, right. So there is a power outflow of this one. So this S Poynting vector, if you take the time averaged value, okay, this will be given by half E cross H complex conjugate, the real part of E cross H complex conjugate. I won't prove this relationship to you. This can be proved easily by actually calculating the electric field and calculating the magnetic field. So what you actually have is that the time averaged power, okay, will be given by, the time averaged power is given by half of real part of E cross H complex conjugate, provided you express electric field and magnetic field by their appropriate phasors, okay. So it is important that you note this is the phasor. The actual Poynting density that you have E cross H, when you do not express E and H in terms of the phasors but in terms of the real R and T dependent field, this one is called as the instantaneous, okay, instantaneous Poynting vector, and this is again a density only, because you go back to this one. So if this is only density, because the total power flow is given by density times the closed surface area. So this is actually power per meter square. So these are all the power density, or that is why sometimes this is called as Poynting power density, and this is a power density term, okay. And the average power density or the average power flowing will be given by half of real part of this. If there is a you want to multiply this one by the surface area of a surface that then you will get the time averaged power out. So this is the density. The actual average power, okay, will be given by integrating this power density over the appropriate closed surface, okay. So if you apply this Poynting vector to the cases that we have already seen, suppose I have an electric field of a uniform plane wave which is propagating along the z axis, but it is oriented along the y axis, let us say. So y hat 100 is the amplitude of this one, cos omega t minus some 20 pi z, okay. So this is an example where, of course, I am not specifying the frequency omega, but the propagation constant is specified as 20 pi into z, okay. What is the corresponding phasor for this? The corresponding vector phasor will be y hat 100 e to the power minus j 20 pi z. What will be the corresponding magnetic field for this? Well, you know that E cross H should point along z, although we haven't really talked about that one. From Maxwell's equations, you know that, so by applying Maxwell equations, you can show that the magnetic field must be oriented along minus x direction and should have an amplitude of 100 divided by eta 0. Eta 0 is the intrinsic impedance of the medium. and this will be in phase, so it will be cos omega t minus 20 pi into z. If you just take E cross H, you will get a term which is going along the z direction or oriented along the z direction, and then you get 100 square divided by eta naught cos square of omega t minus 20 pi into z. But as I said, you are not interested in the instantaneous energy density because you can never measure that instantaneous energy density. The optical frequencies are changing too fast. No detector is able to measure variations of the electric field at that particular time scales of resolution. So you are only always measuring average power integrated over many cycles, and that can be obtained rather easily. You express them in the phasor form. You have already expressed the electric field. Magnetic field will be along minus x hat direction, having an amplitude of 100 by eta, and you will have e power minus j 20 pi into z. Okay. Now what is the average Poynting vector density? S average, that is half of real part of E cross H complex conjugate, right. So this is very easy to find out, half of real part E cross H phasors, right. So there will be there will be a Y phasor coming because of the electric field, okay, cross minus X phasor coming because of the magnetic field. The amplitudes get multiplied, so you have 100 square divided by eta naught. But what happens to the phase? Electric field will have e power minus j 20 pi into z, magnetic field will have e power minus j 20 pi z, but when you conjugate that one, this becomes e power plus j 20 pi into z. These two will cancel. Real part is not really real, no point about that one. So this would be z hat 100 square divided by 2 eta naught watt per meter square, watts per meter square. So this is the average, time average Poynting vector, and this is when you integrate it over the closed surface will give you the total power. So this completes our discussion of Poynting vectors. In case of the power calculation, you just have to follow the equations that are given here. We will have little bit more to say about this in the case study that we will consider. Thank you very much.